Well, good afternoon and welcome to the afternoon session. Our first speaker this afternoon is Abdelmalek Abdesselam from the University of Virginia, and he's going to talk about pointwise multiplication of random Schwartz distributions with Wilson's operator product expansion.
Thank you, Gordon, and thank you to the program as well as workshop organizers for the invitation. This talk is about putting together two topics, one from physics, which is the operator product expansion, a general feature of quantum field theories, which plays an especially important role in the conformal bootstrap approach. That's basically the foundation you start from. And also in probability and analysis, the problem of multiplying distributions. So we know that ever since the introduction of this beautiful theory, in particular by Schwartz, it works well for linear PDEs, but as soon as one tries to multiply two distributions pointwise, one runs into trouble. So here I'm going to talk about this particular case where it's not an issue of multiplying deterministic given distributions, but random distributions, and being able to do that in an almost sure sense. All right, so this is the plan for my lecture. So let's start. So I don't know about you, but I remember the first time I studied calculus and the great achievements for this guy, for instance. It blew my mind, and actually the similar thing happened later on as a graduate student when I opened books in quantum field theory and I saw things like that. These were definitely not in my calculus textbook from first year university. In quantum field theory books, you find this kind of functional integrals or path integrals in the Euclidean signature, which makes it a little bit better. So this is supposed to be an integral over a function phi, which lives in a space of functions from Rd to R. The weight here looks positive, exponential minus some kind of energy functional. This is an example. And z is the normalization constant, so the whole thing looks like a probability measure, and it looks like we're trying to compute moments, expectations of products of evaluations at different points. Now, if you go a little bit further in the quantum field theory textbook, you go to the chapter on renormalization of composite operators, and you see that not only these kind of objects appear, but you also have to consider correlations involving more complicated functions or operators of the field. So for example, phi of x squared, phi double gradient phi, etc. And so ever since the first time I saw this as a student, this raised questions which are still with me now, and these are these questions which I think are important. So and the first question is, how seriously should one take this probabilistic, and it looks like a probability measure, but can it be made into a probability measure in a rigorous sense? Possibly making the field phi a distribution. Already for the free field, we know that you need to do that. What about the composite fields? Are they also random distributions? And finally, composite fields look like they are a deterministic function of the underlying elementary field phi. Is this true or not? So these are the main questions I would like to be able to answer. Well, let's say that I believe the yes, but with some caution. So what evidence do we have? Well, for the elementary field, there has been various constructions, rigorous constructions. For instance, P phi 2, work of Nelson, Green Jaffe, lots of other people. Phi 4 3, also several constructions, but I just mentioned the very last, most recent one, which I'm sure you heard about during this program. There is also the conformal field theory obtained by a scaling limit of the critical 2D Ising model, thanks to the work of all these people. So these all made rigorous sense of phi as a random distribution. What about composite fields? Well, there has been these new theories regularity structures, paracontrol distributions, which essentially I think is a progress in this direction, defining products, pointwise products or powers of these singular distributions. And what I'm going to talk about is a result which you can already find in Archi, which is a theorem for making this type of constructions of renormalized products of random distributions, and it uses as a hypothesis, so something you need to prove if you want to use the theorem, Wilson's operator product expansion. And so this is the subject of the talk. So, I don't think I'll give you a fully precise statement of the theorem, but I'll try to give you an informal introduction. So, all right, the space where my distributions are going to live, typically for me it's S prime, but you can use other spaces of distributions. For example, if you take this type of covariance in Fourier space, well, you can use the Bachner-Minlos theorem to define a Gaussian measure on S prime with that. And here, there is this number here. This is a parameter which I can choose any way I want because I want to also consider fractional models, not just the inverse Laplacian special case. And all right, so there is this probability measure which is well defined and given by that characteristic function. Okay, so now if we try to define the square phi square of x as a distribution, well, that's problematic. So the natural approach is to use a mollifier. So take a function rho, which is compactly supported, smooth, positive for convenience, and normalize so the integral is equal to 1. I'm going to pick a number L bigger than 1. And I'm going to rescale the mollifier using a parameter R, which is integer. So this gives me these rescaled mollifiers. I should state that the smallest scale, so the UV scale in this regularization in position space is delta x equal to this L to the R. So R is going to minus infinity. I'm going to go to small distances. So given this mollifier, you can convolve your original phi, then you make it smooth. This gives me the opportunity to introduce this notation, I think due to Schwartz. So I don't like writing integral dy of a product which doesn't really make sense. On the left is a distribution acting on a test function, but I single out the variable of integration, so to speak, y, and I indicate it here as a subscript. Okay. And so this gives me a distribution which is, so actually it's not a distribution anymore, it's a true honest function. It's a smooth temperate function. It lives in the space, so-called space OM. And let me put a little x to emphasize that it depends on the variable x. Okay, so the naive attempt would be to, take this function, square it, that gives you a distribution. Act on it with on a test function f, and then take the limit where you remove the regularization. Of course, this blows up, but it's not difficult to fix, for instance, using Wick ordering. So in particular, in this case, the correct pointwise square is just obtained by a recentering procedure, so you subtract this quantity, which will diverge. And then you have convergence in every LP. Well, you need a local integrability condition. We'll see that again later. But okay, this defines the square. One can also do this for higher powers or more complicated monomials. You can make with the field phi. The earliest reference I found was an article by Segal in Journal of Functional Analysis, but there is also a preprint by Da Prato and Tubaro where they do the construction in detail. So the way I defined it here, technically this is called a generalized stochastic process, meaning you have a family of real valued random variables indexed by test functions, but you can package, yes?
So, you're not going to comment on this condition on dimensional phi, which seems to be very restrictive, so...
The condition?
tons of theories that are not going to satisfy. So
Yes. So yeah, there is a barrier from if you try to do probability theory. There is a barrier at white noise scaling dimension d/2. I don't know what happens beyond. So my whole talk is going to be below d/2. Yeah. Yeah, that's a good question. What happens when you go beyond? I have no idea. This would definitely involve the so-called contact terms.
What was the question?
I was just wondering if phi squared it only makes sense if the dimension of phi is below d/4. So
Yeah.
the condition there.
Yes. Probabilistically.
Many theories that are not going to satisfy this condition.
So if you want to make it into a rigorous random distribution, I don't know. I don't know if anybody knows how to do it above d/2. Maybe folks in regularity structures and other approaches might know, but I don't. But of course, in quantum field theory, one is not restricted by that. So that the other thing I mentioned is that if you want to do this probabilistically, you really have to understand the contact terms. How it's not just the correlation functions away from the diagonal who are going to give you that information. Anyway, so just a word here. So this is a so-called generalized stochastic process, but you can collate all these real-valued random variables into just one distribution-valued random variable. So you have a map, which is Borel measurable, which goes from phi to phi squared. Okay. All right. So to introduce some terminology, so there is this what I call a pointwise representation. And already this needs to be below the scaling dimension. So the covariance, you can write it as an integral in position space of the test functions times this kernel, which I call the pointwise correlation. And it's so it's an honest function. It's not a distribution, but it's defined outside the diagonal. In this particular case, here is the explicit formula. We're still talking about Gaussian measures. So, all right, if you look at the fourth moment, it looks like this. And the fourth moment also has a pointwise representation of this kind. Okay, so integral of the product of test functions times a certain kernel. And here is the kernel. And so this is seen as a function on what is called configuration space usually. So you take RD, you make n copies, Cartesian products, but you remove the diagonal where some points coincide. Okay, so that's a nice open set, and this is a smooth function on it. Let me introduce another, a new pointwise function. So again, the points have to be distinct, given by this formula here. And so it turns out, I mean, it's easy to check, that you have an asymptotic expansion of the previous pointwise correlation when x1 goes to x2 under the hypothesis that x2, x3, and x4 are fixed. Okay, and so first you have a singular term which blows up, this guy, and after that there is this perfectly finite expression over here plus corrections. Yes?
You started with the assumption that phi, dimension of phi, was less than d/4, and now it's less than d/2? Or
No. Okay. To define the square, you need to be less than d/4. To have a pointwise representation for phi, you need to be less than d/2.
Yes, but here, phi square is not defined if phi is less.
Okay, so you didn't catch. This is, I'm talking about C infinity functions. There is no probability here. On this slide, there is no probability theory at all. I'm just talking about a bunch of C infinity functions on some open set of distinct points. So this is defined. Okay, but yeah, then so this is why you see the previous slide. On the left-hand side, that's probability theory. On the right-hand side, this is just some bunch of smooth functions. Okay, and so to have this equality, this is where you need these conditions on the scaling dimensions. So to have this equality, for instance, you need phi, the scaling dimension, to be less than d/2. Right. Okay, so all right, but so this is an example of what is called operator product expansion, and basically what it says is that inside correlations, so these algebraic objects, these pointwise honest functions, And this expansion says when you see a product like this and x1 goes to x2, this has this kind of asymptotic expansion with a certain coefficient here. This is the field equal to 1 and a second coefficient plus other terms. And in this case, this is what they are. So the non-trivial part of this expansion is that this doesn't depend on the other guys. Phi of x3, phi of x4, you can put a lot more terms there. The coefficients here are always the same. That's the non-trivial statement in the OPE. Okay, so the theorem that I want to talk about is a general black box, which given a set of pointwise correlations which satisfy an OPE, like I just showed, and with precise bounds on the remainder, so the little O of 1 that I showed before, that won't do, we need something more precise. And if you have this as an input, then the theorem constructs a suitable renormalized product of random distributions. So the theorem works for Gaussian, non-Gaussian measures, massive, massless fields. You can have anomalous scaling dimensions, logarithmic corrections. You can have several operators with the same scaling dimension, and you don't need translation invariance. Maybe that could be useful for like space-time distributions in stochastic SPDs, for instance. But first I have to introduce some things. How am I doing for time? All right. Okay, so I'm going to assume that I have already a certain collection of true, honest, random distributions, O sub A, where A is just a label in some alphabet B, and these are honest random distribution valued random variables on the same probability space. I'm going to assume that they have moments of all orders, and so I'm going to also use the rescaled mollifier, but also translate it to put it at any point I want. So, so this type of moments by assumption makes sense. They are continuous linear forms, so they can also be seen as distributions on R n times D. And okay, so what are these pointwise correlations? Maybe one way to define them is to take the approximation where the test functions approximate delta functions sitting at these points x1, xn, if the limit exists. So the first assumption I'm going to make is that these pointwise correlations exist, are smooth functions on the configuration space, so distinct points, and I'm going to assume that kind of condition. So these have to be locally integrable, including on the diagonal. Okay. And moreover, I want the probabilistic objects, so the true moments of random variables, given by smeared, these distributions smeared by test functions, to be given by this kind of integral which features this C infinity function. So, and this is where this kind of hypothesis on scaling dimensions comes in. All right, so that's my first assumption. Now, if you're given a system of these pointwise correlations, just some functions of n points, distinct, you can play around with them as if they were moments, even though they are not. So this is what I call formal. Was there a question? No. Formal multilinear expansion. So for example, suppose that you have some function of two variables which are distinct, which live on this configuration space of 2 points. And suppose I have something like this. Well, that also makes sense in a trivial way. You just expand and say this is the definition. Yes?
Is it essential that we have several of these OAs? Like, to understand the theorem, could we just think of OA being equal to phi that you mentioned? I'm saying, how essential is this that we have several of these OAs? Because I'm starting to get lost in indices. Could we just
well,
equals phi? Is it essential to understand the theorem?
Yes.
Okay.
I'm surprised that you asked the question because you juggle with 20 million fields. Well, it's essential here. I mean, you need to go up to a certain level because you construct fields using the OPE, and so you need to have constructed all the fields which appear in your OPE to extract somebody deep. If you have your OPE deep inside, you want to extract a field, you need to have already defined all the fields with higher scaling dimension which appear, higher or equal. So you need to work with several fields in general. But you can, of course, apply it in the simple case of phi square, and the identity operator. Okay. All right. So is it clear how this works? Okay, you expand. This is a deterministic object, so it's a constant that comes out, and okay, for instance here. Okay, so I will use this. I don't want to define this in a Bourbaki fashion, so hopefully that'll be enough. So I'm going to assume that my symbolic field, well, my actually true fields, OAs, have a certain number associated to them called the scaling dimension, and that governs the singularities on the diagonal. In particular, if you just look at the 2-point function, essentially it should be roughly this power of x minus y. You can also have logarithmic correction, and this is for x minus y small. I don't care about the long distance at this point. Okay, so so there is two parts. There is the kind of the probability aspect where you have a random distribution, and they have this collection of pointwise functions, which I call an abstract system of pointwise correlations. All right, so I'm going to suppose that this system of pointwise correlations satisfies Wilson's OPE, meaning that if I take two operators in my set corresponding to one of these alphabets, I think A, sorry, if inside correlations, this kind of product when x goes to y with everything else being fixed, should have this kind of asymptotic expansion. So these are the new fields produced by the expansion. These are the OPE coefficients, and this is the remainder. So where does this power come from? Well, it's kind of, imagine that there is somebody right after. So the dependence in x minus y is entirely in this guy, and this is essentially, if C had dimension exactly delta, this is exactly what you would get, just by comparing the homogeneity, for instance, near the origin. So if you multiply x by lambda, you have a lambda to the minus this number come out. Here, lambda to the minus b, whereas on the right inside the correlation, you'd have a lambda to the minus delta, and so you need this multiplier to kind of have everything homogeneous. Okay, so this is the main hypothesis of the theorem. Okay.
Hypothesis means this is what you want. Hypothesis is.
This is a hypothesis. You need this to be able to construct the random distribution. So, okay, I'll define. So don't worry, I'm going to show it again. Okay, so there are some quantifiers here. Okay, what's going on? There is an inequality. The inequality is right here. It doesn't show very well, even though I try to highlight it. Okay, so we have some monstrous correlation defined using this formal multilinear expansion, a bound on it. And then this is a indicator function of some condition. So basically, if this doesn't hold, we don't show anything. And this is 0, so it's void. So the inequality is only in force when these conditions hold. And okay, this is the complicated bound. All right, so we have a bunch of points. This is, okay, okay. This is just the usual, norm. So, I mean, non-homogeneous norm, if you want. So this is to control the growth at long distance. That's because I want to work with the space S prime. So, okay, I I allow growth at long distance of arbitrary power. Now I have three types of objects. These were individual fields. Then there are these two things. So here is the definition. So what I call OPE sub I, because there could be several insertion of these OPEs inside the correlation, is basically a product of two fields minus the beginning of the OPE up to a certain scaling dimension delta I. So it's a notation for the remainder of the OPE sitting in there as a bilocal field, so to speak. CZ, what is CZ? Well, it's a term corresponding to moving a field from position X to position Y. Why CZ? Well, it's after Calderon-Zygmunt, because in the theory of singular operators, there is a bound which is very similar to what I have here. So I'll explain maybe more in a sec. And okay, so the previous monster, this is what I call the enhanced nearest neighbor factorized bound, which is kind of a quantitative form of Wilson's OPE, not just little O of something. And the special case, maybe it's easier to start there first. A special case, which I call the basic nearest neighbor factorized bound, is where there is none of these complicated non-local objects, so it's just a bound on correlators. So the bound is basically some constant. You allow some growth at infinity. This is the important thing here. So for every field, you look at the nearest neighbor, okay, the distance to the nearest neighbor, and you have 1 over that distance at the power, the scaling dimension of that field. Okay, and it comes as a product, so that's kind of nice. It's factorized. The little epsilon, that's to allow a little bit of logarithmic corrections if you want. Let's go back to the quantifiers. So the statement is, well, okay, you can find some eta, you can find some gamma, and then for every epsilon, so you want to be able to pinch those logarithmic corrections, there exist these two constants. I didn't have room to put right after that, for every position of the points, provided they're distinct, we have this bound. Okay, so you see, so what's going on? It's, there are 3 sets of objects. So they correspond to the location x's, but then there is a group which I call OPE and a group which I called CZ. And for each one of these, so the x's are like stars. And then the first 2 have kind of their own solar system, so they have their little satellite. So this is x1, and they have y1 here, x2, and a point y2, and same thing here. x10, y10, and these guys are just, they don't have any satellite, any planet. Okay, so first, the condition on the left says that I don't need this bound unless for every solar system, the planet y is closer to its sun than the distance of that sun to the other stars. Does that make sense?
For the first 2 sets.
Hmm?
For the first 2 sets.
Yeah, for the first 2 sets. So if this is not true, then I don't care. I mean, there's no hypothesis I need. It's only in that situation that I need this bound. Okay, and all right, so here we find the similar thing I mentioned. So for every field over here, so individual fields, you look at the distance to the nearest star, so x's, you don't really need the y's. And basically you have a contribution of 1 over that distance at the power of the scaling dimension, and you can allow these logarithmic corrections. Let's do this one first, maybe it's easier. So this is for the CZ terms. So for one of these guys, you again have the distance from this x to the nearest other x appearing at a power which is what you expect, this scaling dimension, but that you need to have a little more, which is this gamma. Okay, so you must be able to find the gamma, so you must be able to get a little more, and this is compensated by this factor which has to do with the distance to the corresponding y. And this is what looks like the typical conditions in the theory of singular operators, singular integrals. You require conditions like that. I think it's called Hormander's condition or standard condition. In particular, that's because those CZ terms formally introduces a gradient. So actually, you even expect this to hold for gamma equal 1, but gamma strictly positive is good enough. And this is also what people use in harmonic analysis. Finally, for the OPE, so for the OPE terms, this is what you get. So, so this is as if there was a field of this scaling dimension. That was the cutoff of the scaling dimension. So it's as if there was a field of that dimension sitting there gamma, so I'm requiring basically a gap in scaling dimensions. So the next higher dimension operators is strictly far away by at least this gamma. And this is what you need to put as far as the contribution of this distance to have the scaling dimensions work. Okay, all right, so we'll come back to this later.
May I ask a question, Malik?
Mm-hmm.
How you arrive at this? You abstracted it from Greek fields or something, and then said, let's assume that it's true.
No, it comes from our result with AJ, I mean, follow-up to that result with AJ and Gianluca on the hierarchical model, and the new technique we introduced, which is this renormalization group for space-dependent couplings. So non-uniform RG in space. Okay, I can say a little bit more, but so you have this, so RD, actually here it was QPD. You have a bunch of points, and you can build a so-called fusion tree, which is kind of a geometric object which depends on the positions. And so there is a formula for the connected correlation function of a bunch of fields sitting there in terms of a certain huge composition of tree-like composition. You know, you plug B of f of x, y, g of something like that. You put the functions of many variables, and these functions, they correspond to, if you look at one node, so that's an L block. So, and you have the parents. So there are L to the D smaller boxes inside the bigger box. You have space-dependent couplings for phi 4, everything sitting at any one of these. And so you have, so the RG is a function which, given the couplings in these guys, gives you the coupling at the next level, etc. And the main object has to do with putting the fixed point values everywhere and then perturbing by test function, which has to do with these points, and see how it propagates. And so the main thing is, suppose that you put an operator just at one box, that gives you an evolution of the coupling, and the coupling, the evolution doesn't have the usual L, this kind of thing. You basically lose the integration. And this operator is what appears along chains like that when you go very deep in the RG. And so basically the factors which appear there, they have to do with these depths until the first fusion. And so that has to do, that basically geometrically corresponds to the distance to the nearest neighbor. And this is, in fact, looks a lot like what people call holography. So I have an explicit representation of connected correlation functions in terms of something which is like the analog of ADS space for hierarchical models. But okay, that's what's behind.
So how do your bounds correspond to what are known bounds in perturbation theory?
Well, you are the expert. I would have liked you to prove this, but I mean, in your work, you smeared the spectator fields with compactly supported test functions in Fourier space, and that destroys the structure. But probably, I mean, should be able to, using your techniques, maybe be able to prove that. But this is purely in position space.
Can you say again why one would want to prove that?
That's the hypothesis of my theorem.
Oh.
And I think so. So one is not one in general. Is it one me? Yeah, I think it's actually a general fact about quantum field theory. So I think something that was missed. Okay, okay, there is maybe I should hurry up. There's still more to say. So, okay, there are some little technical conditions which have to do with working in non-translation invariant situations. So these OPE coefficients, for instance, they have to belong to this tensor product of spaces. Essentially, it means that if you smear this in X with a function in Schwartz space, the resulting object in Y should belong to this space of smooth temperate growth functions. Okay, and all right, so what I'm assuming is that, so here's my Slava's question, collection of fields. This is where I assume that I know this at the level of pointwise correlations. And I assume that this collection is a subcollection V plus one more field. And this is the guy which I would like to construct. I don't know it yet as a random distribution. And the B's are the fields which I already know as random distributions. And so maybe I should just give you the formula. Essentially, what I'm doing is this. So I peel off the field of interest using the OPE up to the scaling dimension of that field. And I divide by essentially that's what I'm doing. And I'm taking the limit y goes to x. Of course, this doesn't quite make sense as it is, but that's just the intuitive idea. You need to smear with these rescaled modifiers, and if you really insist, I'll show you the formulas at the end. Okay, and
Fields A and B has to be below d over 2.
yeah, all the fields.
Well, how many fields do you expect there to be?
Hmm?
How many fields do you expect to be below d over 2?
I don't care. I just need it to be finite. I just.
Normally, they're going to be one field, like at most. There are not going to be many theories where there are going to be more than one field in this range of dimensions.
Well, okay. So the cheated a little bit because the Gaussian case you can lower the scaling dimension of the field to make it artificially lower. You can have as many as you want. Actually, I'm interested in the situation where you can do this with just how to construct phi square. I'll mention that later. So there are 3 fields involved, 1, phi, phi squared. Even that I would be happy, but okay, this is a general theorem which could be of use in other contexts. You see, this is not just for quantum field theory. You can also do it for maybe space-time distributions, provided one has an OPE for SPDEs. Do moments of SPDE satisfy an OPE?
So, stupid question. I just missed one slide and I don't remember what is OC star.
OC star, this is the field which I want to construct. So everybody else.
What is it? We define it.
Hmm?
We define it. Well, on the first slide. Just can you just go back one slide?
So I'm assuming, so these are labels for systems of functions on the complement of diagonal. So there is no probability. So for this abstract system of correlations, I suppose that I have knowledge of these correlations for all labels in this set A, together with the OPE, asymptotics, etc. Now, I suppose that this set A is made of 2 things. Well, there is one special guy, C star. This is the guy I want to construct, plus all the other guys. I'm assuming that for all of the other guys, I already have an incarnation as a true random distribution, a probability measure on S prime. Okay, I already assume that for these guys, but suppose I don't know that this is also, this field corresponds. So this is how to do an induction step to construct one more field. Okay, and the way you do it is you do the OPE up to the scaling dimension of this field, and I'm assuming that everybody else here has been done, so has been defined. And I use this as a definition of OC star. I mean, intuitively. Then you have to smear properly. I'll show you if you want the formulas. Okay, let's talk a little bit about examples. Why do I care? Okay, there are examples, but they're conjectural. So suppose you take a ferromagnetic spin system, okay, with the usual Hamiltonian. So the single site measures could be Bernoulli, so Ising spin, or 5-4 type double well potential. So you can typically, at the critical temperature, want to study the scaling limit, and so you can make 2 random distributions out of that spin field. So the first distribution phi sub r, given by this. So again, L to the r is the cutoff scale. So delta x in the UV, or if you want the lattice, the mesh of the lattice here is basically L at the power R. Okay, so you just transport, I think Martina and Massimiliano, you call that the extension map, if I remember correctly, how you go from, lattice fields to distributions without trying. Okay, so this is for phi. For the square, you do the same thing. You just recenter. Okay, of course, for Ising, you can't take the square, but just the usual energy observable. And so in many cases, one conjectures that this pair of random distributions converges in joint law to a pair of random fields, phi and phi squared. Okay. And so hopefully this gives rise to a system of pointwise correlations if you look at the kernels of their moments. And conjecturally they should satisfy an OPE, and as Slava, so to go back to Slava's questions, I'm already very happy with just this. Okay, and with these OPE coefficients, so this guy, notice that it involves this difference of scaling dimension. So this is actually an anomalous dimension. You don't have this in the Gaussian case. And so you can also read off these numbers, the scaling dimension of phi and phi squared at the level of the lattice. If distributions you're not familiar with, it's just these asymptotics of two-point functions, truncated, of course, for the square. Okay. All right, so there are several cases one can fit into this framework. So there is the short-range Euclidean Ising model, dimension d at least 2. So d here is just the Euclidean distance. The coupling is just the nearest neighbor condition. You can also do the same thing with phi 4 spins instead of Ising. Then there is also an interesting class of models, which is the so-called long-range Euclidean models, where the coupling decays as a power law, so d plus sigma, you need sigma to be positive. And if you think in field theoretic terms, that means that you're replacing the Laplacian by a fractional power of the Laplacian in the Gaussian measure. And so it's known that if you're in dimension at least 2, or even in dimension 1, provided that the sigma is not too big, you get a phase transition. If sigma is too big, then you're back to the short-range case. Actually, there's been a recent work by Slava, Behan, and I think Rastelli, don't remember, yeah, studying this transition to the short-range behavior. And okay, another class of models which I studied and I like a lot, I think Wilson liked them a lot too, is so-called hierarchical models. So the difference is that the distance here is a hierarchical distance. Okay, it involves this structure of small blocks inside the bigger blocks, and how deep you have to go to find your ancestor, etc. With the same formula for the couplings. Okay, so results, so survey of what's been done. So for 2D Ising, the scaling limit has been constructed rigorously, shown to be a conformal field theory with this particular scaling dimension, 1/8. So the scaling limit for phi square, unfortunately, is problematic. So we kind of encounter the problem that Slava raised, that there's not that many fields under d/2. And this is actually a bad case where you're right at the d/2. And as far as I know, we don't know what the scaling limit of the energy field could mean. For phi 4 2D short range, rigorous results, I think nothing is known. Of course, a very important case is the three-dimensional short-range Ising and also phi 4. So conjecture is that the joint scaling limit of phi and phi square should exist, and according to best in 2016, I don't know if it is still best, estimates by folks in the Bootstrap program, these are what the exponents scaling dimensions are believed to be, and notice that this is less than d/2, which is 1.5. So maybe one could use a theorem there if one does the scaling limit. Okay, it proves the OPE. Notice that the difference, so the anomalous dimension of the square is 0.37 according to these. Now, what about the long-range model? So that here we're in better shape. So in the Euclidean case, so the case one where there has been recent work is so this is close to the mean field regime, but in the below the upper critical dimension, which corresponds to taking sigma of this form with epsilon small. And so the recent work of Lohmann, Slade, and Wallace, they proved that this is the critical behavior of the two-point function. And the scaling dimension here is exactly the same as the Gaussian measure you start with, so it's given by this expression with no correction. For the hierarchical version of this result, so this is this paper by myself, Chandra Guadagni. So there we did also the correlation of the square field, and so we showed that this number exists. So this symbol means you're bounded away from 0 and infinity in the ratio. So here we find exactly the same exponent. And this is due to Gawecki-Kupian, and I think even Kohli-Ekman might have showed that. But the result that this number is strictly bigger than 2 times the scaling dimension of the elementary field, that was new. So more precisely, we get we prove this relation, epsilon over 3 plus O of epsilon, which is actually the same as in the Euclidean case up to order epsilon. And that was predicted by Wilson in a not very well-known paper. If you extrapolate to epsilon equals 3, that gives 0.33, which is not that far from 0.37, so the what is expected for the 3D Ising model. So in fact, in that paper, we also did the scaling limit, but it's a hierarchical model, so it's not going to be on S prime of RD. I mean, maybe you can, but it would look very ugly. There is a better space to work with, which involves p-adics. I won't say more. And so the main technique was to do space-dependent RG, and this is where this the basic and also the more complicated bound comes from. It looks a lot like this stochastic quantization, but in the RG language. Not the stochastic, the radial quantization in CFT. And okay, work in progress is to actually prove the OPE for that model. Not complete yet. Okay, so general conjecture is I think that any quantum field theory should satisfy this monstrous bound that I give you. Gapped, so yes, maybe this is not that huge of a restriction. So a gap means that if you look at the scaling dimensions up to a certain delta, there is only finitely many operators which satisfy that. Which are scaling dimension up to delta. Unfortunately, that excludes the Gaussian free field, the massless field in 2D, but okay. And Liouville maybe. But there are experts of that here, so I won't say more. So again, I promised I would show you this monstrous bound again. So I believe this is true. It's not, you don't really need, I think, standard axioms, meaning the Osterwalder-Schrader positivity, so if you have a system of correlations, just play with them and try to see if they satisfy this bound. Actually, an interesting example is for 2D Ising. So if you take the pure phi correlations and you look at the particular case of what I call the basic bound, but without epsilon, so for CFTs you don't need these logarithmic correction protection, and there is no growth at infinity, so let's eliminate them, then this is what the bound means. And in concrete term, we have an explicit formula for these. This is a kind of a high school inequality. Okay, so what is this? So this is an explicit formula for the correlations of the Ising CFT, scaling limit. So you have a sum over charge, neutral charge configurations, plus or minus 1. It has to sum up to 0. And for each configuration, you take the product of the distances with these exponents, and you finally take the square root. That's the correlation. And so the basic bound just says that this is less than product over each point, the distance to the nearest neighbor at this exponent, which is basically the scaling dimension of the spin field. So this is a totally elementary inequality. But not that elementary. It relates to electrostatic inequalities introduced by Onsager and Baxter, used for proofs of stability of matter, etc. There are several beautiful proofs, actually. I think the earliest one is by Fröhlich, using Cauchy identity. There was a nice proof. I don't know if Vincent is here, and Rémi, but it uses the Gale-Shapley stable marriage theorem. I don't know if that was an original idea introduced in that paper, but that's nice. A proof by Heyer and Shen, Furlan and Murat. Okay, but it's also a trivial consequence of the Gaussian correlation inequality of Newman. Well, a trivial modulo the deep work of Shelka, Kongler, Isurov. Okay, so it's a ferromagnetic model. So you have the inequality at the lattice level. You just need to control the limit and show that the correlations at the limit are exactly this type of thing. Okay, so that's the hard part, of course. Maybe how much time do I have? I'm almost at the end.
5, 6 minutes.
5, 6 minutes. Okay. Okay. So if you want an actual example where I check that all the hypotheses work, unfortunately, it's a bit of a trivial example. We lack examples here. It's the fractional free field. So, all right, just to kind of give you an idea of the structure of what's involved. So the fields are labeled. If you've done representation theory, you take you've seen maybe a notion of plathism, take symmetric power of symmetric power and find the basis for that. Essentially, you're taking monomials of monomials. So, for instance, you can label an operator. So the most general operator looks like this, and you can label it. So this is a multi-index for the derivatives. You basically have a collection of multi-indices modulo permutation. Okay, that's your label set. Okay, so the scaling dimension obviously is the R times so the number of fields give you this this contribution, and then each derivation you take the number of derivatives of the corresponding multi-indices. You can define the degree. You can define more generally for any finite set and a function from a finite set to multi-indices. You can also define a corresponding label, the equivalence class up to permutation of the corresponding multi-indices. If you've never seen that, the corresponding abstract system of pointwise correlations, let me just give you right away. So this is just the standard combinatorics of Wick monomials. You sum over so you have a bunch of points. Each one carries a certain number of legs with derivatives on them. You sum over all contractions. That corresponds to this W. So it's a sum over pair partitions of F is the total set which labels all the legs, which comes with a decomposition into F1, Fn corresponding to vertices. The derivatives, once you do the contraction, will hit the products of covariance elements. And the main condition, which has to do with the fact that these are Wick-ordered monomials, is that there is no contraction within vertices. Okay, I'm sure you've seen that. And so I checked that for this system, we do have this type of exactly what I said, this OPE with the precise bounds that I gave you. And so at least there is one example where the theorem can be applied. And so this kind of gives you an alternate construction of Wick, local Wick powers, which were known a long time ago. But for instance, it doesn't use things like hypercontractivity, or it's maybe in flavor, it's a bit more generic as a proof. Okay, so I can give you a formula if you want for the OPE coefficients. Here are references. So the theorem is already on archive. This one is going to appear soon. That has a review kind of for the general context. But the original idea came as a consequence of this work where we introduced this space-dependent RG. That's supposed to be a gentle introduction. Thank you.
Thank you, Malik. Are there any questions?
Yeah.
Yes.
So you mentioned the Ising model in 2 dimensions several times, and then it was constructed in 2016. Wasn't the Ising model, together with all the other minimal models, constructed by DPZ in 1984 or something?
So what do you mean by constructed? In what sense? Are you a probabilist? Are you wearing your probabilist hat or axiomatic CFT hat?
Well,
So as a probability, so as a random distribution obtained as a scaling limit, as I said, of a field on the lattice that is shrinking, this is 2015. So the
gave exact correlation function. Exact correlation function.
And you have exact.
Geometric function, really exact. Coulomb-Gas integrals.
Yeah, but do you know that they correspond to the moments of a probability measure? I think even that is non-trivial.
Okay.
So, which is that square root of some overcharged configurations. Show that these satisfy the Bachner positivity, that you expect for moments. I don't know.
Is there another question? Yes.
I was a bit confused by your remark that now we are supposed to forget about Stromada Schroeder and think about this.
No, so I think that if you play around with, if you have explicit formulas,
Let me
yeah.
know what I mean. So I think what we understood very well from Stromada Schroeder is that correlation functions of all operators are supposed to be distributions in Minkowski. When you go to Euclidean, generally you don't expect for them to be distributions at coincident points. Now you are trying to kind of find a few fields for which you can view the correlation functions also as distributions at coincident points. But why is this a natural thing to insist on? I don't understand the whole logic of it.
I mean, from your point of view, I don't claim that it should be natural for you, but I really want to take these seriously as probability measures on spaces of distributions. If you want to do probability, you need the information on the diagonal. A moment is not just pointwise away from the diagonal. So the condition on being under d/2 is that all the information on the moment, including on the diagonal, is contained on the pointwise correlations outside.
But why should all fields have this interpretation? Why should all fields have this interpretation? Okay, phi maybe does.
I think
but why should there are tons of.
I think I'm an optimist. I don't know. As I said,
No, but why do you expect this is natural? There are infinitely many local operators of arbitrary high dimension. Perhaps a few you will be able to realize in this, but I don't understand. It seems like you're heading for something which is not going to work in general.
Well, I want to see up to where I can go. So the issue, I don't think there is an impossibility to go. A no-go theorem, which is that you cannot go above d/2. For instance, if you take the derivatives, these have. If you have a field and you take distributional derivatives, then you get an honest random distribution of arbitrarily high scaling dimension. So there exists random distributions with scaling dimension way beyond d/2. But taking these products, I don't know how to make sense of them unless I'm below. So to go further, I would need somebody like you, for instance, to give me information about the contact terms, so I would have probability, candidates for moments of a probability measure. So I don't know.
I think we should stop now. So thank you very much again.